Okay, good morning. We'll continue the yesterday's problem. So we have determined the shear force values, and this is how our shear force and bending moment diagram would be for that particular beam. So it was a beam with overhang on one side, and we have determined what is the maximum bending moment in that beam, and also where the point of contraflexion is. Okay, we have located that point of contraflexion. So after this, in drawing the bending moment diagram, what we have is okay. So this is the variation in the bending moment and shear force. Values are at A 213.33, B minus 266.61, and 160. So this is 213.33 kilonewton, 266.67 at B negative, and at this point itself it will also come to 160 kilonewton positive. Okay, and at C it will come to 0. And if we look at the bending moment values, what we have is the bending moment at B. Okay, we are determined. So at A it was 0, C also it was 0, B it is minus 160, and also value of maximum bending moment is 284.46. So what I have here is this is 160 kilonewton meter negative. Okay, and maximum value 284.46. So this is the maximum value 284.46 kilonewton meter. Okay, and what we have, this is our sagging bending moment. Okay, positive moment, and this is our hogging bending moment, negative moment. Similarly, shear force. This is positive shear force as per our sign convention, negative shear force, and here again positive. Okay, so these are the bending moment and shear force diagrams. So this is SFD shear force diagram, and this is BMD bending moment diagram. Okay, so variation in shear force will be linear. Okay, when the UDL is present on the beam, and the bending moment diagram will be varying in a curved manner, in a quadratic manner. The variation should be shown by this curved line. Okay, and the points what we have identified are maximum minimum. Okay, so it will come exactly below this point of zero of shear force. This 284.46 is coming directly below this shear force diagram. This diagram there is slight shift over there, but this point and this point one and the same. Okay, and point of contraflexure is here. This is the point of contraflexure where the bending moment is 0. Okay, so here negative bending moment is existing. What it means is when you look at the bending of this beam, okay, on applying the load, this is how the beam will be deflected. Okay, I'm telling you hogging and sagging. Okay, so in sagging, curvature will be downwards. So for that purpose, we are taking this as positive movement, positive bending moment. Okay, curvature is downwards. In hogging, the curvature will be upwards like this. Okay, so that will be considered as negative bending moment. Okay, so here the curvature is upwards, here the curvature is downwards, bending edge. Okay, this is what it means. Sagging and hogging. This is actually how the beam would deflect or behave when applying the loading. Okay, so that is the plotting part of that bending moment diagram. So you have to plot this bending moment diagram after calculating all the values of shear force and bending moment. Okay, just let me put this for your information. point of counterflexure is here. This is the point of counterflexure. Okay. So maximum hogging moment, if you ask me, it is 160 kilonewton meter. Okay. And maximum sagging moment is 284.46 kilonewton meter. There is negative maximum in terms of negative moment also. Series sagging. Okay. So maximum hogging we have indicated it by negative sign. So if you have drawn the shear force and bending diagram, this is how it should look. You don't have to draw this deflected shape here. That will be covered in different model, deflection of beams. Okay. So here just to understand what is this sagging bending moment and hogging bending moment. Okay. They represent the nature of bending over here of the beam. Sagging means curvature will be downwards like this. Hogging means curvature will be upwards like this. This is hogging portion of the beam. Nature of bending. Okay, this is the nature of bending. Right. So further, let us go with some standard derivations over here. Like what we have is, in case of a simply supported beam, okay, so if this is a simply supported beam, right, and say we have a uniformly distributed load applied on this beam. You may come across such cases, some standard cases of loading, and let's say the span of the beam is L, and this UDL is of W intensity, W per unit length. Okay, so what will be the maximum bending moment in this case? Okay, how will be the bending moment and shear force diagram? You have to calculate the bending moment and shear force diagram and plot the bending moment and shear force diagram. Okay, so what you need to do here is plot SFT and BMT, shear force diagram and bending moment diagram, and also find maximum bending moment. That is what we are supposed to do here. Okay, so for this, what we have, first, if I go for calculating the support reactions, okay, so what I have is, if I take the two support reactions as VA and VB, okay, say this is VA and VB at support B, So this is VA and VB. I'll call these two supports as A and B over here. Okay. So VA and VB, they will be equal to W into L divided by 2. Okay. If you apply the two conditions of equilibrium, you'll come across this. Okay. So suppose if you find the reaction VB by taking moment about A, what it gives you, VB into L, okay, minus VB into L and anticlockwise movement, plus due to UDL, it is W per unit length into the total length is L. It is spread over a length L, where it will act exactly at the center of this length of the UDL into L by 2 should be 0. So this will tell you that VB is equal to W into L upon 2. Okay. From this, it is also clear that VA plus VB, okay, minus W into L. This is summation Fy is equal to 0. Okay, should come out to 0. So if you substitute for VB, what we have obtained here, you will conclude that VA is also equal to W into L by 2 over here. So the two reactions, okay, so they are equal in magnitude. So if you apply these conditions of equilibrium, two conditions of equilibrium, you will get to know what are the reactions. So WL by 2, both reactions will be equal. Symmetric loading, so they will be sharing the load equally, both the supports. WL by 2, half of the total load will be coming to support A, half of the total load will be going to support B. Okay, in case of such symmetric loading on the beam, you'll get the reactions as equal. Okay, there will be half of the total load which is applied on the beam. Okay, in such UDL case, for example, here what we have. Now, what about the shear force? Okay, if you calculate the shear force at A, so it will be VA, which is equal to WL by 2 over here. Okay, left side upward force is positive. From 0, it will suddenly increase to WL by 2. Now, I'll directly come to B, shear force at B. Okay, here I'll take to the right of point B. Okay, just before I cross this reaction to the right of this point B, what is the shear force here? So what are the total forces on the left side of my section? When I have my section over here, okay, at this point, what forces I'll come across to the left side of the section over here? So I have taken that section over here. Okay, so this is my section, what I have. Okay, so in that case, to the left of my section, I'll consider the algebraic sum of the forces, what are there. So what I have VA over here. So VA, which is left side upward force positive, and this UDL is there. What is the total UDL? W into the span of the UDL, okay, into the length of the UDL minus W into L. So this will be the shear force over here, okay, which is equal to what? I'll just continue here, WL by 2 minus W into L. So this will give you the shear force, okay, at A as minus WL by 2 over here, okay, minus WL by 2. So shear force at B, it is coming out to be minus WL by 2. Once you cross that support left of B, when I come to left of B, it will be equal to VA so that is VA, okay, VA minus W into L plus VB. Okay, now I have crossed the this support over here. I brought my section somewhere over here to the left of this point B. Okay, now this will be my total shear force over here. So that will be equal to how much? In this case, it will be 0. It will come out to 0 now. So this will be equal to WL by 2 minus W into L plus WL by 2. VA and VB are WL by 2. So this comes to 0. Okay, so this is the shear force at different points on this beam. So under such loading condition, some standard loading condition, when the beam is carrying uniformly distributed load for its entire length. Okay, so simply supported beam carrying UDL over its entire length. For this, if I want to find out shear force bending moment diagram and also determine what is the maximum bending moment, what we are doing here is this. Okay, I've taken the beam. Okay, and on this beam, UDL is applied for the full length of intensity W per unit length. Okay, so now what I have done first is we have followed the same procedure for calculating bending moment and shear force. The first step is to find the support reactions. Okay, so we got the support reaction VA and VB as WL by 2 on applying these conditions of equilibrium. Now after a calculation of support reaction, the first thing what I have done is I have considered a section at A. Okay, so I have taken a section, this section over here. So I have taken this section and placed it at A. When I am to the left of A, shear force is 0. No need to calculate that. So there are no forces on the left side of my section. So shear force is coming 0. When I slightly move to the right of this point A, what happens to the left of the section? What are the forces coming over here? I have this reaction coming in picture. Okay, so shear force at A, I can say VA is equal to VA, which is WL by 2. Okay, when I place my section over here, so it is WL by 2. Shear force at A is WL by 2 now. Okay, after this, what I did is I directly moved to point B. I took my section at this point to the left of support B over here. Okay, so there, what is the shear force over here? For that, what you require is you need to go with taking the algebraic sum of all the forces to the left of your section. Okay, to the left of my section, what I have is there is VA, left side upward force, positive. So VA, and this UDL is present over here on the left side of the section. So total weight due to UDL, what is the total load? W into L. W intensity per unit length into total length, W into L. So VA minus W into L. Minus W into L because it will be acting downwards. Left side downward force, we will be assigning a negative sign for that. So the shear force when my section is to the left of support B like this, the shear force is coming out to be minus WL by 2. Okay. After this, what I did was I moved further. I placed this section where to the right of point B. Okay. Now what all forces are coming over here on the left side of the section? Here what I have is totally the VA is there. Okay. And what I have, this is all the forces what we have over here. All these entire forces, left side, VA, UDL, and support reaction at support B. Okay, so I'll be taking sum of all these forces. Okay, then it comes out to be what? Here, VA minus W into L plus VB. These are the forces which are there on the left side of my section in this portion. Okay, so VA WL by 2 minus W into L, this total load to the UDL, and VB WL by 2 plus WL by 2 because left side again it is upwards. It is directed in an upward direction. Okay, so that is how I got my shear force at B here. So now in this case it is coming out to be 0. It is reducing to 0 once I cross this reaction. So we have the values of shear force now. And then we'll move ahead with the calculation of bending moment. So what I know is at 2 points at support A and B, the bending moment value will be 0. Okay, these are the end supports and I don't have any couple applied at these points. So here I can directly write that my bending moment values are 0 at support A and B. Okay, so once I have that calculation, now we'll try to find where the maximum bending moment will come. Okay, so where is the point of maximum bending moment in this beam? So how do you find the point of maximum bending moment? For that purpose, we'll apply this relation. Okay, what is the condition for maximum bending moment? For maximum bending moment, the condition is that dm upon dx should be 0. Okay, and what we have is also dm by dx is nothing but it is equal to f. Okay, f is what? F is shear force at x, at any distance x, shear force. Okay, so what I can do is I can directly equate shear force to 0. Therefore, for bending moment to be maximum, shear force value has to be 0. Okay, this is what I know from the condition now. Okay, even what you can do is you can write the equation for bending moment m in terms of x. Okay, so m will be a function of x like this, and you can differentiate this with respect to x and equate it to 0. That will also tell you what is the value of x, the point where maximum bending moment is. So instead of working it in a mathematical way, what we'll do is we'll try to relate it with this with our forces. Okay, so here I am relating maximum bending moment with the shear force. So the point where bending moment is maximum, the shear force will be 0 over here. Okay, so let us find first where the shear force is coming out to be 0. Okay, so the variation of shear force we have seen from plus WL by 2 to minus WL by 2. It is changing from point A to point B, from positive to negative here. So somewhere in between, it is coming 0. It is coming to 0 over there. So it is between A and B. Somewhere in between A and B, our shear force is changing the sign. Okay, so let us take one section somewhere between A and B. Okay, I don't know at what distance it is changing. So our job is first to determine this distance x where the shear force is 0. Okay, so I'll take this section 1 1. I'll place a section here at some distance x. Now I'll write what is the value of shear force at this distance x. Okay, so if I want the shear force at this distance x here, so it will be equal to shear force at x. Okay, so at any point x on the beam. So it will be equal to VA, left side upward force is there, VA positive, minus due to UDL, it will be W into X. Now this UDL is covering only this part X, okay, only up to the distance X we are considering. So this comes out to be WL by 2 minus W into X. What I want is this should be 0 for maximum bending moment. I'm interested in finding where shear force is 0. So this will give me what is the value of x. So what x should be on this? What is the value of x we get over here? It is
1
uh-huh. Is it
L by
1?
2
It comes out to be
L by 2.
L by 2. So what it tells is exactly at the center of this beam, the bending moment is maximum. Okay. So exactly at the center of the beam, L by 2. L is the span of this beam, L by 2. Exactly at the mid span, bending moment is maximum. And at that point, the shear force is 0. So therefore, what we have is, what is the maximum bending moment? So bending moment 1.2 we noted is, bending moment is maximum at the mid span. Please note, this is for this particular case of loading. Okay, simply supported beam carrying UDL for its entire length. Only UDL is there. For this particular case, this is what we have. Bending moment is maximum at the mid of the span. Okay, what is the maximum bending moment value? So maximum bending moment. Now we'll try to find that. So again, I'll take movement of all the forces to the left of this section. Okay, I'll consider all the forces to the left side of the section, and I'll take movement of those forces to about this section. So what I have is VA into L by 2. X is L by 2, or you can write X and then later we'll substitute that L by 2. So VA into X, okay, left side clockwise, I have taken it as positive, minus W into X by 2, okay, or it is WX square by 2. So here what I have, WL by W into L by 2 into L by 2, this is my X value, minus W into L by 2 into half of L by 2. Okay, so this is the maximum value of bending moment. What this comes out, WL square by 4 minus WL square by 8. What it will be? 1 by 4 minus 1 by 8. How much it comes out? WL square is there into 1 by 4 minus 1 by 8. Is it WL by 4? Do you get WL by 4 in that case? Check it. I've taken moment of all the forces to the left of section about this section 1 1. What are the forces over here? I have VA over here. So this is VA into X clockwise movement. Due to UDL, what is that? W into X by 2 minus W into X by 2. It is having anti-clockwise movement about this section over here. Okay. If you are not getting, you have to just imagine the free body diagram. That particular section. This is our section 1 1. Okay. What forces are applied? This is WL by 2 PA. Okay, and also along with this we have this UDL W, okay, per unit length, and this is X, value of X we have got it. Okay, so what is this? VA into X clockwise. Okay, so sign convention we already had for shear force. This is the sign convention, positive. For bending moment, this is the sign convention. Okay, recall this sign convention, positive. Left side clockwise movement, VA into X, left side clockwise movement, so plus VA into X. Due to UDL, W into X by 2. This entire resultant of UDL, W into X, will act exactly at the center over here. Okay, center of this UDL. Okay, so W into X by 2. So this will be the value of maximum bending moment. Okay, is that clear? So in such case, what I can write, formula for maximum bending moment in case of simply supported beam carrying UDL, maximum bending moment will be equal to WL by, how much we got? WL by 8 or 4?
4.
Square by, this is,
4.
yes, 1 minute. This will come out to be WL square first of all. WL square by,
8.
yeah, 8. Is it right? WL square by 8?
Yes.
Calculation. Okay. So this is WL square by 8. Right? So this is the maximum bending moment in a simply supported beam. And what is the value? WL square by 8. Okay. So this is what we have. How is the variation here? So if you look at the variation, what we have is the shear force and one for the bending moment diagram. These two lines are representing our beams. Shear force here it is WL by 2. Okay. And on the other end at B, what it is happening? Minus WL by 2. Okay. So because of UDL, the variation will be linear from here to here. Okay. So this is WL by 2 positive. Okay. At point A, WL by 2 negative, and this is point B. Okay, this is what we have. This is SFD for that simply supported beam carrying UDL for its entire length. Okay, and one more diagram what we require is this bending moment diagram. Okay, so exactly at the center, the shear force is becoming zero. It is changing the sign, and at that particular point, it is becoming zero. So here we are getting the maximum value of our bending moment. Okay, which is WL square by 8. So this is the variation of bending moment. Okay, it will be curved, and entire bending moment is sagging in nature. That is, this is positive. What is the maximum value? WL square by 8 is the maximum value. At A and B, moment is 0. This is our bending moment diagram for a simply supported beam with UDL, carrying UDL. Okay, so we took a standard case. Okay, for a standard case, this is what the standard case was: simply supported beam carrying UDL for its entire length, and we determined what is the maximum bending moment in this particular case, and we have also plotted that. Okay, so the thing you have to remember is, for a simply supported beam carrying UDL for its entire length, the maximum bending moment is WL square by 8. And where it will occur? At the middle of the span. Okay, at the middle of the span. That is the important point what we have to note in this case. These are some standard results. Is that clear? I hope everybody has understood this formula, what we derived. Some standard relations. One more such case is when a simply supported beam is carrying a concentrated load. Okay, I want you people to try these cases. I'll give you the beams. Okay, procedure is same. Okay, procedure remains the same. What is the first step? Calculate the support reactions. Okay, then take a section from one end. Okay, it may be from left end or right end, that is from left support or right support. Okay, so convenient ways we have followed a procedure that will move from left to right. Okay, so in that case, this is the load what is there. Okay, so this is concentrated load over here applied exactly at the middle of the span. Intensity is W, or magnitude is W here, not intensity. Magnitude is W. So this is L by 2 up to this point. Okay, and this is L by 2. So this concentrated force is present exactly at the middle of the span. Okay, so for this, what would be the maximum bending moment? Can you find out that? This is, say, VA, and if this is support A, this is support B, BB. Okay, point C, the load is applied. Total span is L, L by 2 plus L by 2. Load is applied exactly at the center of the span. What are VA and BB equal to? Due to symmetry, it is placed exactly at the center. So each support will be taking half of this total load. Okay, so only under such cases, if you are not sure, go for applying condition of equilibrium and find out what are the support reactions, two support reactions. Okay, now try calculating the shear force values. Okay, shear force values, and then go for finding the maximum bending moment value. Okay, we require maximum bending moment value. For that, first you have to find out where the shear force is coming out to be 0. And what is the equation for maximum bending moment in this case? Reactions I have given you. If you want to verify that on your own, if you want to do it, check it. First, summation Fy equal to 0, you can write that equation, condition of equilibrium, then take moment about point A, find Vb, and you'll also get to know what is Va equal to. Check and tell me whether it will come out to be WL by 2 or something else. I was telling you what steps to follow is find support reactions, place the section, go for finding the shear force values by taking algebraic sum of all the forces to the left of the section. Okay, wherever required, you have to place the section. Okay, and when we come across such concentrated loads, we are considering two sections to understand what is the change in the shear force, sudden change in the shear force. Okay, please try this one. If you are able to do this, the concepts of this shear force and bending moment will be clear to your mind. Okay, if you work on such non-numerical problems, numerical problems will become much more simpler. Okay, dealing with the numerical problems would be very simple. But thing is, you have to apply your mind in this particular part. You have to work on such problems. That will help you a lot. I'll give you these two standard cases for your this one as your assignment. In this case, what is there is this is distance A. Okay, the load is not placed at the center. You please work on first one. Later you can look into this second problem. The two distances are not same, E and B. Two. And this is the total span L. Okay, one is this as your assignment, two is this one. Please keep on working on this practice problem and assignments what I have given. Later you will have to submit them. Okay, for these what you have to do, draw shear force diagram and bending moment diagram. Also find maximum bending moment value in terms of equation, in the form of equation. Okay, so try these two. Okay, you try it. The solution I'll give you later, but I want you to try, and next class you have to tell me that equation of maximum bending moment. Okay, for first one and second one, for first problem and second problem. Let us see how many of you can turn up with that. Okay, genuinely try it on your own. Doesn't matter if you go wrong. You can leave your USN in the chat box, attendance. If you require, take this screenshot, keep it with you for derivation. Give the attendance and later you can exit. I'll finish it over here. Yes, if anyone is having doubt, 19CV76 has raised the hand. If you have any difficulties, you can tell me. Total 1976. If not, if you are given the attendance, you can exit.